today we're working on a partial differential equation. This is the heat equation, which is one of the classic partial differential equations that we like to solve in differential equations for engineers, which is normally taught in the math department in the partial differential equations part, I believe. So the base form of the heat equation is actually already up here for us. So that's going to be a heat constant times the second order partial derivative of our base function with respect to x, and that equals the first order partial derivative of that same base function with respect to t. Now, the method that we use to deal with this kind of partial differential equation is going to be separation of variables for partial differential equations, which should feel really familiar to partial differential, or for ordinary differential equations, separation of variables. There's just one little trick we need to make them separate. So we're going to start with this here, where this u of x of t is equal to capital X as a function of x, and then capital T as a function of t multiplied together. This is going to be the key to how we're going to start separating these out. And then over here we have all of our initial conditions that we're going to use for this particular example, which will come in probably about halfway through. So we'll go ahead and just get started by starting with this equation, taking our two partials with x and our one partial with t, so we can start plugging stuff in here. So we can start, just this k just goes here. The second order partial derivative of this function with respect to x, this t becomes just a constant, so we're just going to take our partials with respect to this x. In this case, we're just going to use prime notation. We don't need to do anything too crazy. So we're just going to have x double prime of t. And this is where I'm going to stop writing the small x's and small t's, just because that gets really cumbersome and it is not particularly urgent to do. And then we'll take our first partial with respect to t of the same function, so we'll just have capital X of t prime. Now, to do separation of variables on this, this one's pretty straightforward, so we're just going to divide everything out by all of our constant terms, so our k, our t, and our capital X. So we have k, capital T, capital X, which this is going to turn into capital X double prime over x, and that equals capital T single prime over k capital T. So now we're going to switch back from this prime notation to Leibniz notation just to make it a little bit more clear of what we're doing. So we have d capital, I'm going to use capital X first, like I originally wrote, not capital T. So we have d capital X second order over, then this is just going to be d little x, and then it's still multiplied by the big X, and that's equal to d of capital T, and that's over d of little t of capital T times k. And then this is also, the second order derivative. That won't be super important, but just it's easier to keep track of what we're doing with our dt's and stuff if we write it in this notation. Now, in order to actually split these apart, we're going to use what's called a separation constant, or separation variable, and we're going to use negative lambda. I don't remember if there's a specific reason why it's negative lambda, but this is related to eigenvalues and eigenvectors, so we're actually going to find the eigenfunctions of this PDE. That's part of what this process is. We're just doing it in a different way than we did in our linear algebra video. Okay, so from here, we're just going to take each of these individually with this lambda term, and if we set both of these equal to lambda, we know that they still equal to each other because they both equal the same negative lambda. So that's the way we're going to attack this. So we're going to start with this partial of t first, because that one's a little easier to deal with, because that's just a first order ODE. So we have our d of dt, d of little t, capital T, k is equal to negative lambda. Pretty straightforward. So here, we want to keep all of our big T's together, and then we'll take our little t over here. If there was other t's, they would be over here as well, but this is all we got. So we're going to take little t and k over to this side, and then we'll leave our t's together. So here we'll have d capital T over capital T, and that's equal to negative lambda k d little t. And now from here, this is a just regular separation of variables with the first order, so we can just do a direct integral. We don't need to do anything super fancy, nothing super crazy, just straight integration. So integral of 1 over capital T is just going to be natural log of capital T. And then on this side, we're going to pull out our constants of negative lambda k. So we have negative lambda k. And then the integral of dt is just going to be t. And then remember, this is an indefinite integral, so we do need to keep track of that plus c. And we're just going to call that c1. So now here we need to get t by itself, so we're going to take everything to the e power, and that's on both sides. So then this left piece here just becomes t, which is equal to e to all of this stuff. And then since we have this addition here, we can distribute our e across. So e to the c is still just a constant, so we're just going to pull that constant down in front. So we have c1 e to the negative lambda kt. Okay, so that's our equation for t. Now we're going to write that off to the side. We'll come back to it here in a little bit, but then we're going to move on to our double prime. So we have t is equal to c1 e to the negative lambda k little t. Okay? Now, the next one's a little more challenging. So here we're going to take this second order differential equation equal to this negative lambda. So for this case, I'm going to go back to our prime notation just because it's a little cleaner. But it's still the same thing that I'm doing. So I have this is all equal to negative lambda. And the reason I went back to this particular notation is because this is the separation of variables in the partial differential equation, but for this ordinary differential equation that we're dealing with here, separation of variables is not going to work. We're actually going to need to use our auxiliary equation and some other stuff. So let's get to that form first. What we're going to do is just multiply this x over. So we have x double prime. And if I multiply this x over and then add it back over, so we have plus lambda x is equal to 0. And that's where we're at. So now from here we can go to our auxiliary equation. So we have m squared, because this is a second order derivative. Now this is a 0th order derivative, so this is just going to be plus the constant, and that equals 0. So now in this case, we need to figure out our cases of lambda that in order to solve the three different possibilities that exist here. And those possibilities are when lambda is equal to 0, when lambda is less than 0, and then lambda is greater than 0. So to accomplish that, we're going to use lambda equal to 0. That one's pretty straightforward. We're going to use lambda is equal to negative alpha squared. And then I'm going to write it here in the middle, but it doesn't really matter. We'll evaluate them all. Lambda is equal to alpha squared. So let's deal with this lambda equals 0 case first, because I think that's the most straightforward. So in this case, we're going to have, I'm going to write it over here. We'll do the math over here, and then we'll store everything on this left. So for lambda squared, we have m squared plus 0 equals 0. So we have m equals plus or minus the square root of 0, which of course is still just going to be plus or minus 0. Now, this may be something where you're tempted to just say, oh, well, that doesn't matter at all. It does still matter, because this is actually going to be real repeated roots. And so when we have the case of real repeated roots, we now have that our capital X is going to be equal to C1. And then real repeated roots is where you take e to the thing, t, and then we're going to do plus C2 of e to the thing t. So the 0 in both cases. And here's the thing. When you have the exact same thing twice, you always have to put an x in front of the next one. And if we had a third one, we would put x squared. And if we had a fourth one, we would put x cubed. And we would keep going. And that is actually how the solution for the real repeated roots works. Okay, so in this case, this is what we get. Now, of course, we know that e to the 0 is just going to be 1. And then we know that x times e to the 0 is just going to be x. So this actually works out to just be c1 plus c2 e. Sorry, not e, x. Okay. So this is now our equation of x, capital X sub little x. Now we can plug in our initial conditions and see what our constants are. So let's start with our initial condition where x is equal to 0 right here. So when x is 0, we get that c1 plus c2 plugging in as 0 for this x, we get 0 here, and we know that needs to equal 0. Okay, so this term already has a 0, so this term already goes to 0, so we're good here. So c1 is equal to 0. Well, if c1 is equal to 0 and this term's equal to 0, well, everything's equal to 0. Well, and if everything's equal to 0, this is not working as well as we'd like. But we have to do our other condition real quick, because this isn't saying that c2 is 0, this is saying that c2 times 0 is 0. So we still have a possible c2. So let's see if that eliminates on this other one. So if we have x of L is equal to 0, we're plugging in L for x in this case. So now we have c1 is already 0, so that term's gone. So now we have x times c2, and that equals 0. So for this x, we're going to plug in an L. So now we have L times C2 is 0. Well, L can't be 0, because if it is, we're just back at this original initial condition, so that just doesn't make any physical sense. So in that case, since L can't be 0, then therefore C2 must equal 0. And so now that we know that C1 and C2 equal 0, this is lambda equals 0 is trivial. That's the trivial case. Right? It doesn't actually help us with our solution because of our initial conditions. Okay, so we'll write lambda equals 0 is trivial. Okay, let's erase all this and do our next case. Okay, that t stays there, don't erase that. Let's put a little box around this so I don't accidentally erase it. Okie doke. So in our next case, let's do lambda equals negative alpha squared next. So we have m squared, and then we're plugging in negative alpha squared for single lambda, so that's going to be minus alpha squared equals 0. And so now we can solve this algebraically by adding this alpha squared over. So we have m squared is equal to alpha squared, and we can square root everything. We get m is equal to plus or minus alpha, just alpha, sorry. Now, plus and minus alpha is not real repeated roots, this is real distinct roots, because negative alpha and positive alpha are different. Plus and minus 0 is the same thing, that's why you get real repeated roots. This is not that. Okay? There's some algebra to get here, but basically the way this one's going to work out is going to be, we're going to have x sub little x is equal to constant times the hyperbolic sign of alpha x plus another constant times the hyperbolic cosine. I said those backwards from how I was writing them, but they're both true, so it doesn't matter. Okay, now we can plug in our initial conditions. So if we plug in 0 for our x's, like we did earlier, so we're plugging in 0 for x, and we should get 0 as our final value. So we have C1, the hyperbolic cosine alpha times x is just 0, and then we have plus C2, hyperbolic sine, and then alpha times x when x is 0 is still 0, and that should equal 0. Okay, so hyperbolic cosine does equal 0, but it only equals 0 once. So in this case, this is going to go to 0, and hyperbolic cosine goes to 1. Okay, so now we know that C1 is equal to 0. But in this case, C2 can still be equal to something else because sine was the thing that made this term 0. And 0 times anything is 0, so C2 can still be something else. That's the important part to understand here. Okay, so now let's do our other condition where we're plugging in L for our little x. And C1 is 0, so that term's gone. So now we just have the C2 term. So we have C2 sine, hyperbolic sine, times alpha L is equal to 0. Now here's the thing about hyperbolic sine. It's not like regular sine where it hits 0 multiple times every period. This only ever hits 0, so hyperbolic sine is only 0 at 0. And therefore, since this is only 0 at 0, in order for this term to be 0, and we can't plug in 0 here for L again, because again, we've already plugged in 0 for our spatial component. So in order for this whole term to be 0, C2 needs to be 0. And again, since C1 and C2 equals 0, the lambda equals negative alpha is going to be a trivial case. Okay. Now we can do the last one. And I did them in this order because I think it's pretty obvious, but we're going to have a term that's maybe not trivial this time. So this last case that we're working on is going to be the lambda equals alpha squared, positive. So we're going to take this m squared, and then this is plus lambda. Lambda is positive alpha squared, so it's plus alpha squared, and that's equal to 0. Let's add this alpha over to the other side. So we get m squared is equal to negative alpha squared. Take the square root of everything, and we get m is equal to plus or minus. So the square root of negative alpha squared is just going to be alpha times I. So this is going to be our complex conjugate pair of differential equations back from really early on in your differential equations course, which works out to be capital X little x is equal to C1 cosine, regular cosine, not hyperbolic cosine here. And then this is going to be our alpha times x, and then that's going to be plus C2 regular sine of alpha and x. And this should feel pretty similar so far because it kind of is similar to the last one, but them being regular cosine and regular sine matters quite a bit. So let's solve our first initial condition here. So we have x, where we plug in 0 for all of our x's. So then we have c1, and then cosine, when you multiply x times alpha, you're going to, where x is 0, you're going to get 0. And then you have c2, plugging in a 0 for x here is just going to get us sine of 0. And then we know that that needs to equal 0 based on our initial conditions. Okay? So cosine of 0 is just 1, so then we know that's going to turn into 1, and sine of 0 is 0. So in this case, we have again that c1 times 1 is just c1, and that whole term here is 0, so the c1 equals 0. Now recall again, the c2 term does not necessarily have to be 0 for this term to equal 0, since sine of 0 was already there. So now let's go to our next initial condition, and we have capital X, where we're plugging in L for little x. c1 is 0, so this term's already gone. So we're just left with the c2 term, and then we have sine of alpha L, because we're plugging in L's for our x's, and we know that this, according to our initial conditions, needs to equal 0 as well. So here's the thing. We don't ever want to make our constants 0 unless we have to. So we're looking to see how can we make this sine 0. Well, we know it's 0 at 0, but we can't use 0, we've already used it. But we also know that sine is 0 every time alpha L is equal to a positive integer multiple of pi. So we know that alpha L equals some positive integer times pi. That'll make this sine 0, which will give us a value for c2. So this is the ratio we need here. And what we're going to do is we're going to move this L over, so we get alpha by itself. Since we're using alpha in a lot of places, we'll be able to plug it backwards. So this is just going to be some critical piece of information we'll need for the rest of the solution. So now we have alpha is equal to n pi over L. And that is so important that I'm going to write it down. So alpha is equal to n pi over L. And then recall our other relationship we called was lambda is equal to alpha squared, right? That's the case we're using here. Okay, so now in this case, this is what makes sine equal to 0. So that means c2 can be whatever we need it to be. So c2 is still a constant. We don't know what it is, but we know it's not 0. So this case is good. So now we can take our capital X, little x, which is equal to some constant times sine of alpha x. And that's our x equation here. So we're going to multiply this x equation by our t equation in the next step, but I'm going to clear myself some space to do that. Okay. So these equations, or these problems are particularly long, and they can be challenging because there's a lot of steps, and it's very easy to make errors at any step throughout. And really the best tip and trick is just to be careful and go slow and write everything down. Don't skip too many steps. And that's really going to be your best path to success here. So sine of alpha x. Okay. Cool. So now we've rewritten that, and now we can start multiplying these together. So the reason we're multiplying these together is because this u function that we declared earlier to be able to separate the PDE was x times t. So now that we have an x and we have a t, we're going to multiply them together. So we're going to have u of x and t again, and that's going to be equal to c1 e to the negative lambda kt times c2 sine of alpha x. And that's it. So this is going to be what we're going to start working with for the rest of this problem. We already know we can plug some stuff in for alpha, we know we can plug some stuff in for lambda, but we have one more initial condition we need to deal with, and then we're going to make one small change to our constants just to be able to see where we're going with this here in a moment. So this will make sense probably in a few steps, but I'm going to set c1 and c2 to equal b sub n. And we'll get to why that makes sense here in a second. But we're going to go ahead and plug in our other initial condition while we do all that as well. So we're plugging in our t equals 0 condition, which if you see at this top right is going to be over the entire length of this rod. We have our initial condition is an f of x. All that to say, we now have b sub n. Now if t is 0, this exponential term turns to 0, and then we're just left with this sine alpha x. And then we know that this is going to be equal to f of x. So wherever we need to plug in f of x, that's the equation we're going to use. And so I'm going to rewrite that over to the sides. We have f of x is equal to b sub n sine of alpha x. Okay, good equation to have. Our next step here is going to be we're going to be using the property of superposition here in order to do a summation of a bunch of these, and that's how we're going to be able to get a value. Since we have some sort of sub n, we need a bunch of these in order to estimate the function throughout the entire rod. We need to be able to estimate the heat throughout the entire rod using essentially what's going to be a Fourier series. So the way we work that out is just going to be that u of x and t is equal to the summation of integers starting at 1 and going to infinity of this function, this b of n times all this other stuff. So we have b sub n of e to the negative. Now I'm going to go ahead and plug in lambda here. So our lambda was alpha squared, alpha was n pi l, so I'm going to have negative n pi over l squared times kt. And then I have sine, and then alpha here is n pi l, so I have n pi x over l. And now this bn term is already defined for the sine expansion of the Fourier series, and that's normally defined as f of x, sine of x, and that's an integral. So this is the half range because we're going from 0 to l, which gives us 2 over l for this particular coefficient of the Fourier series, and we have 0 to l. And then inside we have the function of x is here. I'm missing something. Oh, it's just f of x. That's what goes here. Okay. So f of x goes here, and then we have sine of n pi x over l dx. Okay? And so if we were given an initial condition function, we would actually be able to plug that in for our f of x. Which I will do an example of that here in just a minute. We're going to finish through this one first, though. So if you wanted to, we could go in and we could plug in b of n here into this formula and have a long version of the Fourier series. But instead of doing that, we're just going to move into the example where I use an actual function. Okay. So let's consider this function where we have, let's say f of x is x squared from 0 to pi halves. I think that'll work. Okay, so using that function, we're going to go and solve this Fourier series now. So I'm not really going to touch this top piece just yet. I'm going to deal with this coefficient first, and then we'll plug the coefficient in and solve the top piece. So b sub n is equal to 2. Now our L here is pi halves, so we have over pi over 2. And then we have the integral of 0 to pi halves. And I'm not going to really simplify anything until after I get it at least written out once. So now I have x squared times sine of n pi x. And remember, for L, I'm plugging in this pi over 2, so that goes here as well. And then that's all with respect to x. Okay, so now let's do a quick simplification, and then we can start working on solving this one out. So pi over 2 as a denominator to 2 becomes 4 over pi, because the pi over 2 flips. We still have our same integration bounds, nothing changes there. X squared doesn't change, but sine does change a little. So this 2 is going to come up, and then these pi's will cancel, so we'll have 2n times x, and that's dx. So now we have an integration by parts situation here, and this one is actually a little bit longer than some of the other ones we've seen. So this one will take an extra row than maybe what we're used to. So we have plus, and minus, and then our derivatives are x squared to 2x to just 2, and then to 0. And then our integrals are going to be the sine of 2x piece, or so sine of 2nx. And then our first integration becomes negative cosine of 2nx divided by 2n. Let's take the derivative of the inside and divide. And then the integral here is just going to be negative sine of 2nx over 4n squared. And then our last integral is going to be positive cosine of 2nx over 8n cubed. And then just like normal, we're going to go across and down and across and diagonal. and across the diagonal. Okay, so for our first one, we have a positive and a negative, so we're going to have 4 over pi, big parenthesis, times negative x squared cosine of 2nx over 2n. And then our next piece is going to be this negative and negative, so that's plus. And then we have 2x, and then sine, and that's still 2nx inside, and that's divided by 4n squared. And then this last piece is positive, positive, so we get another plus. And then we have 2 times cosine, so we have 2 cosine of 2nx all over 8n cubed. Okay, and all of this is going to be evaluated from 0 to pi halves. Okay, good. That looks right so far. So, a little bit of simplification and evaluation at the same time. So I'm going to rewrite my bounds for every single one because I can do some mental simplification along the way. So we know cosine when we plug in 0 is going to be 1, so that's fine. Cosine when we plug in pi halves, that's going to be cosine of n pi x, so nothing really, or n pi, so nothing's going to happen there that's going to cancel it out, except when you plug in 0 for this x squared, this whole term will be 0, so this one's 0, right? When you plug in 0 to this x, this becomes 0. When you plug in pi halves to sine, you get sine of n pi over 2 times 2 is just going to be n pi, so sine of n pi, every time you have sine at an integer multiple of pi, you're going to get 0. So that one cancels out completely. And then this one doesn't have that x term in front, so the 0 does not automatically cancel. We already know this pi halves isn't necessarily going to cancel, so we're going to stop there. There's nothing else we can do to simplify our bounds. So we at least killed 3 of our bounds. That's nice. And then I can also pull out a 2 from everything and an n from everything. I'm just going to pull out the 2. I don't think there's any value in pulling out the n, because pulling out this 2 simplifies my coefficient a little bit. But you don't have to do that either if you're not comfortable with it. That's totally fine. Okay, so now we have the negative. I'm going to put outside of a set of parentheses, and now I'm going to evaluate. Well, I only have one bound to evaluate, so I don't need to do all that. That's extra work for no reason. Okay, so plugging in pi halves, you get pi squared over 4 times cosine of 2n pi over 2. And all of that's divided by, we already pulled out a 2, so this is just n on the bottom. Okay, and now we're going to add. So this is 2, okay, so this is 2 over 2, because we pulled out 1, 2, so this is 2 on bottom. These 2 will cancel, so we just have this x sine over n squared. So we're plugging in 0 and 0, so we're not even going to worry about that term. This whole term's gone. We'll go to this last term. We pulled out a 2 here, so this is 4 divided by 2, so this is 2n3 on bottom. So I'm just going to do 2n cubed and 1, and then multiply that by my evaluation here. So my evaluation works out cosine 2nx, so that's cosine 2n and then pi halves, minus cosine of 0, and then I can evaluate. I need one more set of brackets to match. Good. Okay, so now we have 2 over pi. We'll do more simplification algebraically in a minute. I want to focus on these trig functions first. Okay, so we have negative pi squared over 4n, and then cosine of n pi. So every time cosine is at a integer multiple of pi, it's always going to be equal to a 1 or a negative 1. And because it's starting at n pi, where n is going to be greater than 0, it's going to start at negative 1. So we have negative 1 alternating series. And then that's just this whole piece right here. Okay? And now we're going to add 1 over 2n cubed. I know I could simplify out a 2. I will in a minute. Right now we're just focused on trying to simplify the trig parts of this. So we have this cosine of n pi thing again, so we're just going to go ahead and go straight to our simplification we already know. And then minus cosine of 1 is just 1. Okay? Let's see. So for these, we're going to get, so we have 2 pi squared over 4 pi n, and there's a negative here, and that's times negative 1 to the n. And then we have plus distributing this 2 over pi n cubed times negative 1 to the n minus 1. Okay, so we have some simplification that happens here. This 2 and that goes to 2, and then this pi cancels one of those. So we get, we're going to suck this negative in as well. So we now get pi over 2n times negative 1 to the n plus 1. And then over here, there's no algebraic on the outside. If I wanted to swap these around, I could. I don't really see the value in doing that for this problem, so we won't. So we have 2 over pi n cubed, negative 1 to the nth, minus 1. Okay, and so this is our b of n term. So this is b of n. So I'm going to write over here, b sub n is equal to pi over 2n times negative 1 n plus 1, and that's added to 2 over pi n cubed times negative 1 to the n minus 1. Okie doke. So that's b of n. Now we're going to plug that in here, and we'll see if we can do anything else. We may not be able to do much other than simplify just a little, but that's okay. Okay, I'm going to switch to a new color because that one's starting to fade a little. So we've got, I need to refill it, I guess. Okay. Okay, so we've got our summation here. So we have the summation of integers starting at 1 and going to infinity of our b of n term, which at the moment I'm actually just going to write as b of n because there's no other simplification that's going to happen if we combine b of n with these other two terms. Nothing's going to really simplify there, so we can just leave it as b of n just for right this moment. And then we're going to focus on e to the negative n pi over, now remember our L is pi over 2, and all of that is squared, times kt. And then we have sine of, again, n pi, and then x divided by pi over 2. So we can simplify this one time for the one time. So we've got this 2 coming up, these pi's cancel, so now we have e to the negative 2n squared kt, and then that's multiplied by sine of 2nx. Okay, and now all we have to do is just add in our b of n numbers, and we're pretty much done here, I think. I don't think there's much else we're going to be able to do. So we have summation from n equals 1 to infinity, and then b of n is pi over 2n times negative 1 n plus 1 plus 2 over pi n cubed times negative 1 to the n minus 1, and then times all of that is multiplied by e to the negative 4n squared kt times sine of 2nx. And in this case, that actually is basically our answer for this problem, since we weren't given a specific number of n's to do a partial summation on. So we really don't have much else we can do here. We could try and do some algebra here to get some of these constants come in front of our summator, but that's really just an exercise in algebra at this point, and it's just not particularly worth our time. So we don't need to worry about that at the moment. So yeah, this is the heat equation for a rod where the function of the spatial function is defined as x squared, and we're going between 0 and pi halves. Our initial conditions were that at each end there was no heat, and that at time equals 0 we had this function describing the heat along that length. But yeah, there's nothing else we can really do with this, so that was the whole thing. Now I'm not really sure what to work on next, because that was really all I wanted to get done today, and we actually got through that pretty quick. Huh. Honestly, it's the day before Thanksgiving. I might just call it an early night then. I don't know what else to really work on right now. I don't have any homework due, which is normally what I would do on these Wednesday streams, is work on homework, so I guess that's it.